Taylor series. This is a big deal in, certainly super important in the history of mathematics. I think I mentioned last time maybe. The development of Taylor series specifically, this is about power series, but it's a certain way of using power series. The development of Taylor series was a big advance in terms of being able to calculate things. Of course, they were doing this like in the 1800s, still doing everything, all these calculations by hand. But it turned a lot of things which were very hard to do into things which are still kind of hard, but a lot easier. Anyway, the idea of Taylor series is trying to express ordinary functions as a power series. And so far, we have discussed one example of this, which I don't necessarily expect anybody to remember, but it is this. This is kind of like the simplest possible power series, where just a power series in which all the coefficients are ones, all right? This power series here, we have talked at length about convergence of this power series. Does it converge or not, and what is the interval of convergence? Those are on the homework for tomorrow also, right? I think so. Anyway, we've talked about the interval of convergence. What we have not talked a lot about is what does it actually add up to? And this one in particular, you can add them up. This one is geometric because every term is just the next power of x. And in this case, it's geometric where the a is 1 and the r is x. The a is, remember, just the first term. And then the r is what's the ratio of 1 divided by the next one. And you can see here every time the ratio of, I said it wrong, it's the next one divided by the previous one. In this example is always x, right? And so that means this actually adds up to the old formula a over 1 minus r. So this one, when you add them up, you get this. 1 over 1 minus x. That's because the a is 1 and the r is x. All right. So that power series actually does add up to this function. When you're talking about Taylor series, you actually think of it more like the other way around. So this function, 1 over 1 minus x, has a power series. And what it is this. 1 over 1 minus x is equal to 1 plus x squared plus blah, blah, blah. And where does this converge? You can, like we did last time, many examples, we calculate the integral of convergence. And in this case, it converges for this one when absolute value x less than 1, right? This is the, it's because it's a geometric with r equals x, and the geometric series converges when the absolute value of r is less than 1. And in this case, r is x. All right? So that function has this power series. All right? This, from the point of view of power series, this is like everybody's favorite function, even though in other contexts, this doesn't seem to be a very nice or special function at all, but it actually does have a very nice special power series. But the big thing that I want to talk about for our remaining time together is just like your favorite other functions. Do they have a power series, and can we figure out what they are? All right. The first example we're going to do is e to the x. I don't know if this is everybody's favorite function, but is there a power series for e to the x? Can you somehow figure out what the series are? So the big question is, given some function, f of x, what is the power series which adds up to f of x? I mean, can you actually figure this out? Or maybe, I mean, maybe there is no such thing for certain functions. It may be too much to hope for that you can always do this with every function. But anyway, this is the idea. if I have some function in mind, can you figure out what the power series is? So up at the top there, you can see the simplest example. If the function you're thinking of is this, it happens to be that the power series looks like that. But for some other function, say e to the x, what is the series going to look like? And how could you figure that out? Figure out what it comes down to is we want to, we'll need to find each of those coefficients, the c's, right? Each cn. When I say what is the power series, that's what I mean, is tell me what those constants there are. Of course, you're not going to try to find x or anything like that. This is a function, and I expect the x's to remain. It's just these constants that you want to find. So we'll need to find each of the cn's. All right? And one of them is easy to find if you know what the function is. One of them is easy. C0 is always easy to find. We can just plug in 0. Plug in x equals 0. And look what happens up here. What do you get if you plug in x equals 0? Well, on the right-hand side, actually all of these guys, they all become 0 because you're plugging in x equals 0. And all that's left over is C0. So if you plug in x equals 0, on the left side I get f of 0. That's because I plugged in x equals 0. So everywhere up there, I'm just going to replace x by 0 wherever I see it on both sides. On the left, it'll say f of 0. On the right, it'll say C0 plus C1 times 0 plus C2 times 0 squared, etc. All of those things, everything in that dot, dot, dot is all 0. And so this just says f of 0 equals C0. This is a little, I don't know, I prefer to write it the other way around. Since what I'm trying to talk about is how do we figure out what the c's are? The answer here is, well, at least C0, the first one, is easy to figure out. If you know what f is, C0 is equal to f of 0. All right, so this is how we find, this is what I meant by saying C0 is easy to find. All right, so C0 is easy. If you know what the function is, you just plug in 0, and that's all there is to it. All right, what about the other ones? Now, you got to be a little cute about this, but there is a cute trick to finding C1. All right, now, when I just plug in 0, all of these guys go away, and all that's left over is C0. What if I want to find C1? The idea is somehow I would like to do some kind of operation here which perhaps decreases the powers on x every time, which would have the effect of turning this C1 into a constant, the constant part, like putting the C1 in the position of C0 and moving the C2 in the position of C1. Anybody got an idea here? I'm trying to be a little suggestive in my language here. Is there some operation that you could do, perhaps do something on both sides, which has the effect of kind of decreasing all the powers by 1? This is the idea. Some operation. Yeah?
Take the derivative.
Maybe take the derivative on both sides. This is the cute trick. So I'm going to start from here. So I'll say to get the C1, take the derivative on both sides. So you start with, I'll just write again what I started with, f of x equals C0 plus C1x, C2x squared, etc. And I'm going to take the derivative on both sides. So on the left, we just get f prime of x. That's the derivative. On the right, what happens to these numbers? Can anyone say what happens to the C0? I am taking the derivative. Yeah? It goes away, yeah, because the C0 is a constant. There's no x there, so the C0 goes away entirely. Next, C1 times x. I believe when I take the derivative of that, the answer is just C1, right? Because it's a constant times x. The derivative makes the x disappear. I get C1, all right? What comes next? Can anybody say what's the derivative of the next part? The next one is not going to be 0, but it's something. Somebody want to shout it out? Maybe you're shouting it out in your hearts. What do you think? The derivative of this? I'm sure somebody knows. This is not a trick question. Yeah?
Wouldn't it be 2 times C2 times X?
Yes, 2C2X. I hope that's what you all were saying in your hearts. 2C2X. Yeah, I agree. What about the next one? I didn't write the next one, but remember this, the next one would have been C3X cubed, right? And then the next one here, you would do 3 comes down to the front, 3C3X squared, and so on, all right? This is what happens when you take the derivative of those guys. And now I'm going to do the same business that we did before, and that is plug in x equals 0 on both sides. What does it say now? On the left, f prime of 0. On the right, c1 plus 2c2 times 0 plus 3c3 times 0 squared. And again, all of the higher terms there inside the dot, 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 they're all going to be zeros. And all that we get on the right side is just C1. So C1 is f prime of 0. All right? And we have figured out how could you find a C1. If you already know the function f, how can you find C0 is just f of 0. And now we know also C1 is f prime of 0. Isn't that cute? How can we find C2? The answer is you just kind of do it again, right? To find C2, you would take the derivative a second time. Can we try that? So now you may be tempted to think just each of the C's is just equal to the next derivative. It's actually not that simple, and you'll see exactly what happens. What about another derivative? Do the derivative again to get C2. Now, to do the derivative again, I really have to start right there, right? Don't use this guy, which already has values plugged in. There are no x's left over at this point, so you can't take the derivative again. But right here, we can take the derivative again on both sides. On the left side, we get f double prime of x. On the right side, very similar things will happen. The C1 being just a constant will go away in this step. Next, I have 2c2 times x. Taking the derivative here gives me 2c2. 2c2. That comes from the derivative right here. Sorry if I'm scribbling too much here. 2c2 times x, when you take the derivative, that x becomes a 1 times 1, so it's 2c2. The next term, I guess, will be 6c3x, because I multiply, in the next term, I would multiply the 2 down to the front here, it becomes 6c3x. 6c3x. And then some more higher stuff, right? Maybe just for the sake of continuing here, could we write just one more term? The next one, if I had written it, would have said 4c4x cubed. That comes from taking the derivative once. And if I did the derivative again in this step, it would now say the 3 comes down and multiplies on the 4. This will now be 12c4x squared. I'm going to be a little suggestive again here. Rather than writing the 12, it is 12. I'm going to write it as 4 times 3 for reasons that you'll see in a moment. All right. Anyway, that's the second derivative. And again, I'm going to plug in x equals 0, which makes all of the things with x's disappear, and all that's left is something involving C2. Again, we plug x equals 0. It now says on the left f double prime 0, on the right 2c2, and then everything else becomes 0. And this is how you figure out what c2 is. You have to divide the 2 onto the other side. c2 is 1/2 f double prime 0. All right? I don't know if you felt like you knew what the pattern was before. Were you expecting the 1/2? This is a slight complication, but if you look at what we've seen so far in the boxes, C0 is just f of 0. C1 is f prime of 0. C2 is 1/2 times the second derivative. All right. Let's just do one more, the C3, and then maybe we'll be able to see what the pattern is. For the C3, I need to take a derivative one more time. We're not just going to do this all morning, but I want to do enough of these so that we can kind of figure out what the pattern is. So I'm going to do the derivative again here. It now says f triple prime, the third derivative of x. And on the right side, 2c2 is a constant, so that goes away. Next, 6c3, that's what it'll be, right? The x will become a 1. So this is now 6c3. 6, of course, where did that 6 come from? It came from a 2 in one step and it came from a 3 in one step here and then times a 2. This 6 it is a 6, but where it came from was it was a 3 times a 2. Anyway, 6c3, and then plus the next one, if I were to write the next one, was here, 4 times 3 c4 x squared. This 2 will come down and join the coefficient, so now this will say 4 times 3 times 2 c4 times x. All right, and then some other stuff. This 6, I would encourage you, like I just said, I'm going to write it as a 3 times a 2. I'm writing it like that maybe just to help see what the pattern is. Can you see the pattern in those numbers which are appearing? Perhaps you can. Anyway, when we plug in x equals 0 here, it now says on the left side f triple prime of 0, on the right side 3 times 2 times c3. So c3 is 3 times 2 is 6, so this is really 1/6 f triple prime of 0. All right? So there is some kind of weird pattern in these coefficient numbers. C2 gives you 1/2. C2 gives you 1/6. Anybody want to guess what the next denominator will be? It's always 1 over something. So generally, can you see the pattern? Well, there's a pattern here. Maybe before I say generally, I'll just say similarly. What would the C4 be? Anybody want to guess what the next one would be? Yeah? Yeah, she said 1 over 24 f, the fourth derivative, which we usually write like that. Yeah, why'd you say 24? It is this number here, 4 times 3 times 2. All right, what would the next one be? It would be 5 times 4 times 3 times 2. This is the pattern. All right, 1 over 24. Actually, there's a cuter way to write this. If you know this 24 comes from 4 times 3 times 2. Anyone know a cuter way to write that? 4 times 3 times 2. Yeah?
Is it 4 factorial?
Yeah, this is a factorial, which is super important when doing Taylor series. So this I would typically write as C4 is, I don't have to write another C4 there, 1 over 4 factorial. That exclamation, this means 4 factorial, and that means 4 times 3 times 2 times 1. The times 1, of course, doesn't do anything. So that's the same as 4 times 3 times 2, which is exactly what we got here. And the next one would be 1 over 5 factorial. These factorial numbers, they come up, they're not so often, but they come up a lot when you're talking about power series for this reason, because they appear in these formulas here. All right, so in general, Cn, the formula for the nth coefficient, if you do this, if you want to calculate as many coefficients as you want, the nth coefficient always has this format, 1 over n factorial f the nth derivative at 0. So that little parentheses n up there means the nth derivative at 0. All right. And this even works like when n equals 1, like C1, this will say 1 over 1 factorial. 1 factorial equals 1, because it's just 1 times nothing, just 1. And then f, the 1th derivative, the first derivative. So this would say C1 equals just f prime of 0, which is what we already said in the box up there. And even C0, this is something slightly weird, but this would say, if you plug in n equals 0 here, it would say the 0th derivative, which I think of as just being f itself, not taking any derivatives, and that's just f of 0. And then it'll say 1 over 0 factorial. I'm going to say this works even when n equals 0 if 0 factorial equals 1. I don't know if you ever thought about this, but this is sort of a fact or a convention, if you like. Mathematicians generally consider 0 factorial to equal 1, which seems strange, but it's because it works out nicely in formulas like this if you say that 0 factorial is 1. All right. Excellent. That is the formula for the coefficients in a power series. All right. All of this has been a power series centered at 0. This is something that we talked about towards the end last time. You can also consider power series centered at another number. That's when you write the series, so like this one here is centered at 0 because every term just has a power of x. Centered at another number has terms with powers of x minus a, where a is some other number. You can do all of this business even if it's centered at some other number. I don't want to go through all the details, but if you do exactly the same tricks, I'll just tell you what it comes up with. So we can do the same tricks. You could work all this out on your own if you really want to. For series centered at x equal a, remember that looks like a series like f of x is c0 plus c1 x minus a, c2 x minus a squared. All right, this is what I mean when I say a power series centered at some other value. The exact same tricks will work here, and we'll get, this is sort of a what they call a generalization of what you see in the box up here. What's the difference if instead of centered at 0, you have centered at a? The only difference is this 0 here becomes a a. So it works out very nicely. Cn will be 1 over n factorial f, the nth derivative, at a. All right? So if you are trying to calculate these coefficients, they involve taking the derivative over and over again. And in the case of centered at 0, you plug in 0 every time. In the case of centered at some other point, you plug in a every time, whatever that other point is. All right? So I'm going to summarize all this in a theorem, and this is really one of the most important theorems, I would say, like in the history of modern mathematics. Oh, it's not exactly a modern theorem. This was in like the 1700s, I believe. But anyway, this is called Taylor's theorem. And it says, if your function f of x is differentiable, of course, if you want to do this at all, this whole trick is based on taking the derivative over and over again. And if your function doesn't, if you can't take the derivative, then you can't do any of this. But if your function is differentiable, by that I mean you can take the derivative as many times as you like, not only like one time, but all the derivatives exist, then the power series of x centered at x equal a is f of x equals c0 plus c1 x minus a plus c2x minus a squared, etc., where, here's the real deal, this formula, this is just what I said before. And this is really the important part of the theorem. It tells you how to find the constants in the Taylor series, how to find in this power series, how to find these coefficients. And when you are finding these coefficients in this way, this power series is called the Taylor series. So this is called the series that you get by taking these derivatives is called the Taylor series. All right. This is called the Taylor series. Super important in the history of calculation, really, because these coefficients, if you know how to find these derivatives, you can actually calculate the coefficients. All right. If you are just using a equals 0, then all of this becomes simpler. So I'm just going to say usually we'll use a equals 0, in which case then it looks like it's simpler. It just looks like f of x equals c0 c1x plus c2x squared plus blah, blah, blah. And in that case, the formula simplifies, well, it looks pretty much the same, only you use 0 every time instead of a. All right? And this series is sometimes called, although I don't say this all that much, but this series, like specifically when you use a equals 0, this series is called the Maclaurin series. Maclaurin. So sometimes if these, like, to me, I kind of call all of these the Taylor series. If you approach me in public and ask me about, if you show me this, I'll say, oh yeah, that's the Taylor series. And you'd be like, no, isn't that the Maclaurin series? And I'd be like, well, yeah, okay, that's the Maclaurin series. So Maclaurin specifically means you're using 0 here. More generally, the Taylor series also includes situations when you use the a here, all right? Most of what we do is going to be the Maclaurin series. There are reasons why you want to choose a different a sometimes. Like, for example, if the function you're talking about is not differentiable at x equals 0, then you can't do it using the Maclaurin series. And there are some important functions like that, like, for instance, the natural log of x is not defined when x equals 0, and so you can't do this using x equals 0, but you can still do it, say, using a equals 1 or something. All right, anyway, this is the Taylor series and the Maclaurin series. And I will point out one last thing to say about this. Each of these has a certain radius of convergence. Or I will say a certain interval and therefore radius of convergence. All right, so our goal for the rest of our time together is basically just, if I give you a function, you find me the Taylor series for that function. It amounts to calculating each of those coefficients. And as a follow-up question, also tell me what the interval of convergence is. So those are the kinds of things that we are going to be doing. Let's just try, as promised, I want to try f of x equals e to the x. All right? What I mean by that is, let's find, how about this? Find the Maclaurin series. When I say find the series, really what that amounts to is just figure out what the constant coefficients are. And this one is particularly easy to do. You'll see why. This involves taking the derivatives over and over again, right? Involves doing, Cn equals 1 over n factorial f, the nth derivative, plugging in 0, right? That's sort of what we have to do one by one. And for most functions, the hard part really is doing this nth derivative over and over again. It's a pain to just take the derivative again and again and again for many functions. Although, maybe you can see where this is going. That is not such a pain for e to the x. That's the great thing about e to the x, is that it's easy to take the derivatives over and over again. So I need to do the derivatives. Of course, I start with f of x equals e to the x. I'm just going to try to write down the first derivative and the second derivative and the third derivative. What is the derivative of e to the x? It is e to the x. Yeah, everybody knows that. What is the second derivative? That means you just go here and take the derivative again, but you're going to get e to the x again, etc. Right? So when you're doing a typical problem, usually you want to work out a few of the derivatives until you see what the pattern is. And in this case, the pattern is immediately obvious. The pattern is you just always get e to the x every time. All right? So generally, the pattern, what is the nth derivative of x? It is e to the x, right? Every derivative, over and over again, you're always just going to get e to the x. So what is the Taylor coefficient? So Cn, which is 1 over n factorial f, the nth derivative of 0. We just determined f, the nth derivative of x, is e to the x. So when I plug in f, the nth derivative of 0, it shall be e to the 0, right? That's what that is when I plug it in. So I get 1 over n factorial e to the 0, because that's what f, the nth derivative, is e to the x, and when I plug in 0, it's going to be e to the 0. And of course, e to the 0 is 1. So I got Cn is 1 over n factorial times 1, which is just 1 over n factorial. All right. This is basically my answer. If I say find the Maclaurin series, these are the coefficients. So if I were to write out the series, so the series is e to the x is, the first one is 1, and then 1 over 1 factorial x, 1 over 2 factorial x squared, 1 over 3 factorial x cubed, etc. Right? Every time I'm writing what those c's are in here. Every time it's Cn times x to the power n. So 1 factorial here. All right. If you like, you could write it as a summation. This looks like each term is just 1 over n factorial times x to the n. Here's, you have to start n equals 0. All right. That's the series. This is the Taylor series for e to the x, or more specifically, this is the Maclaurin series for e to the x. All right. And it's kind of cute looking. I mean, it's just the reciprocals of the factorials in front of powers of x. All right. It's interesting to me that this is something, you get a very, like I said, a very sort of cute and satisfying pattern here. This is kind of a new way of thinking about the function e to the x. This is a pattern and a structure that, like, nobody, before somebody worked this out, nobody knew this about this function e to the x, that e to the x can be expressed as a series like this. But it gives you a new kind of a way of looking at what e to the x is. The traditional view of what e to the x is, like the original definition of the number e, was something like the limit as n goes to infinity of that, right? This is very unwieldy to deal with if you ask me what the number e is. It's that limit, which is a very strange thing, and if you wanted to calculate this by hand, it's not clear exactly how you would do that. Although, if you know this series, it means that, so the number e, another way you could write it is just by plugging in x equals 1 here. what it says is 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, right? And this actually, if you wanted to, you could calculate this by hand. Of course, it's a series, so it goes on forever, but you could say take the first 10 terms here and calculate them by doing like long division of the fractions and just add them up. You would never actually want to do this in real life, but you could do this. Versus finding this limit is way harder. Even if you say go out to n equals 10, you would have 11 to the power 1 over 10. And the power 1 over 10 is like the 10th root of the number 11. And how would you do that by hand? The answer is, I don't know how I would even start doing that by hand. But this you have a much better handle on, because it's just, these are ordinary fractions, and you can, if you really had to, you can actually add them up. All right? So this is why like the Taylor series produced kind of like a revolution in calculations of things, because it allows you to do these kinds of calculations only by adding fractions together, which is it's a pain to do, but at least you can do it, unlike things like this, which are kind of permanently unwieldy. All right, this is the series for e to the x. Can we talk about convergence? Where does this series converge? Like actually, this will only work if it really converges at x equals 1. Hopefully this does converge at x equals 1. So let's try, where does it converge? And this is really a question just like the ones that we were doing last time. And I hope you remember the standard approach is to use the ratio test. So we're going to do the ratio test. This is always how we figure out the interval of convergence for any power series. All right, and the ratio test, remember, was you do this L thing. L is the lim of the absolute value of an plus 1 divided by an. Now would you mind if I call them C's, just because when we're talking about Taylor series, we always call them C's. But we do have a formula for CNs and CN plus 1s. I wrote it, you can see it at the very top there. CN is just 1 over n factorial, right? So this looks like, sorry, I should have written n's rather than c's. It's not just c's what I want, because the you'll see what I mean. The a's includes the x also, and that's important. You need to include the x because finding where it converges is all about the x, right? So you must include the x's also. An plus 1 is 1 over n plus 1 factorial times x to the n plus 1. That's an plus 1, and then I'm going to go divided by an, which is 1 over n factorial times x to the n, right? Those are my individual terms. You got to take the whole thing, not just the c part, because remember when you do this interval convergence thing, you need x's in there. All right. Simplify these fractions on fractions here. This is the same as I have. This I could think of as just x to the n plus 1 over, I need absolute values, over n plus 1 factorial. And then the other one would be the same but without the plus 1s, and I'm going to write it in the reciprocal. It'll look like n factorial over x to the n. And now we would like to simplify that as much as possible. This is very similar to what we were doing last time. Put the x's together. X to the n plus 1 over x to the n. And then also this other thing, the factorials. N factorial over n plus 1 factorial. We never had to deal with factorials last time. Don't worry about it. It'll be fine. Anyway, that first part just becomes x, right? What about them factorials? How do you, anybody familiar with the factorials? What can we do with n factorial divided by n plus 1 factorial? Any ideas? There are actually some like simplification rules concerning factorials, although I don't know if you've ever learned them. It's not all that complicated if you think a little bit about it. Perhaps I would write out, maybe I'll put this sort of in a little sidebar here. What is n factorial? Remember, n factorial is n times n minus 1 times n minus 2. And I don't have enough room in my little sidebar here. I'm going to move it down. Times, all the way down to times, 2 times 1, right? That's what factorial means. You start with that number and then you multiply it by all of the other numbers that are less than it. That's what n factorial is. What is n plus 1 factorial? That's what we see in the denominator here is I want this divided by n plus 1 factorial. So n plus 1 factorial is actually almost the same. I'm talking about something like, if n was 4, I'm trying to compare what's 4 factorial versus 5 factorial. The difference is you start with one higher number. So n plus 1 factorial starts with n plus 1, and then you go times the next number down, which would be n, and then times the next number down, which would be n minus 1, times all the lower numbers down to times 2 times 1, all right? If you're dividing these, they are almost entirely the same, right? Like this part is the same as that, right? So if you are making them in a fraction, you're just going to cancel those two things. The only thing that's left is an extra n plus 1 in the bottom. All right, so this is a rule about n factorial divided by n plus 1 factorial. Everything here cancels except n plus 1 in the bottom. N plus 1 with no factorial there. It's because the top is the product of every number up to n, but on the bottom we have the product of every number up to n, and then also n plus 1. So they cancel, all those ones up to n will cancel, but we have an extra n plus 1 at the bottom, which doesn't cancel, and that's why it sticks around. All right? Okay, how do we finish this off here? We get, this is sort of my little sidebar here. 1 over n plus 1 is just a constant in terms, not a constant, sorry. This is lim, n goes to infinity, remember? Something slightly weird happens here. This limit is 0, all right? X times that other thing, but when I take the limit as n goes to infinity, that fraction becomes 0. And this just straight up equals, you could say absolute value x times 0. It is 0, all right? I don't think this actually ever happened in our other examples that we did last time, but it is possible that x can be, that L can be 0. L can never be negative. If that happens, you did something wrong, because L, by its nature, has absolute values around it. So it's not ever going to be a negative number, but it could be 0. This is like the smallest that L could ever become. What's your interpretation of this? Remember, you say it converges whenever L is less than 1. But in this case, we've shown that L is always less than 1, right? No matter what x is, L is equal to 0. And so that means it converges no matter what x is. For every x, it converges. So in this example, I'll say here, L is always, I mean for every x, less than 1. So that means that the series converges for all x. It doesn't, because the x went away while we were calculating the L. That means the x ended up being irrelevant, so it always converges for all x. All right. So if I asked you, just for technical reasons, if you like, you could say the interval of convergence is just this. The open interval from minus infinity to infinity. That is, it always converges for every real number. If you insist on writing that as an interval, that's what it is. And the radius of convergence, I suppose, is infinity. All right. So this is what we say in the case when the series always converges. The interval of convergence is all real numbers. If you want to write it as an interval, it's minus infinity to infinity. And the radius would be how wide that interval is measured from the middle, which I guess would have to be infinity. All right. Great. This is all kind of a long-winded example for e to the x, which is the everybody's favorite example of a Taylor series. I looked up some history of this. So in around 1750, our buddy Euler, one of the greats of all, one of the goats, as the kids say these days, Euler calculated the number e using the series to 23 digits. And what that involves is actually writing down the fractions of 1 over each of the factorials and then adding the fractions together and doing a long division to write out the decimal digits. This, like an ordinary person would not ever want to do that, but it's not hard. It's just, it'll take you all day. But, and this was, much better than previous methods that existed. All right, great. In our remaining time, I would like you all to try another function. Try f of x equals sine of x. Can you do it? Do the same business. So write out derivatives until you see a pattern. In the previous example, all the derivatives were the same. They were all e to the x, which made it easy. This one, they are not all the same, but you should be able to do the derivative again and again until you see a pattern, and then try and write the series. Just write the series. Maybe we'll all talk about the interval of convergence together. But I want you to see if you can work out the coefficients. Everybody's kind of getting stuck at the same point, but I didn't really intend for you to try to, in this example, f the nth derivative of x, I would say don't try to write a formula for that, because there's not a nice easily expressible pattern for that. But you can still write down what is C0, what is C1, what is C2. And if you write down enough of those, I'm sure that you will see what the pattern is for those coefficients. That's what I would trying to get you to do. can we chat about this? I see some people are kind of getting stuck. Maybe I should have done another example before telling you all to do one. Here's what I wanted to see though. I mean, people seem to be doing okay with some coaching here. First of all, I would just write down a bunch of derivatives until I can see what the pattern is. So the original function, this is like the zero derivative, is just sine x. The first derivative is cosine x. The second derivative is negative sine x. The third derivative is negative cosine x. The fourth derivative, I'm trying to just do this until I see what the pattern is. The fourth derivative, I'll write it like this. What's the next derivative? Derivative of negative cosine? Yeah? It's positive sine x. And then the fifth derivative, actually now I'm kind of in a loop here, right? These four are kind of the ones that are important, and then after that it's just going to repeat the same pattern. All right, so that's what the pattern is. You get sine and then cosine and then minus sine and then minus cosine, and then that pattern of four things repeats as you continue to do more and more derivatives. All right. Okay, these are the f's, the various derivatives. Now what I want to find is the CNs. The CNs involve plugging in 0 to all of these. So I am going to plug in 0. F of 0 is something, F prime of 0, F double prime of 0. This is what I want, and I would like to say what's the pattern there. So sine of 0 is the first one. Sine of 0, which is 0. The next will be cosine of 0, which is 1. Then I have minus sine of 0, which is 0 again. The third derivative, minus cosine of 0, that's negative 1. And those four numbers will repeat again for the next four derivatives. So the pattern here of these numbers is 0, 1, 0, minus 1, and then it'll repeat again, 0, 1, 0, minus 1, etc. Again, there's sort of this pattern of four things in a cycle. All right? And so, what are the actual C's? The C's look like, Cn is 1 over n factorial times the nth derivative plugging in 0. We know these guys, they alternate in this pattern, 0, 1, 0, minus 1, 0, 1, 0, minus 1. So when I write out the series, it's 1, the first one is 0. So I'll write sine x on the left side. The first one is 0 because the first of these constants was 0, right? That's the first one. The next one has a 1. It also has the factorial part though. So the next one is plus 1, but it's 1 over 1 factorial times 1. And then plus, the next one is it's 1 over 2 factorial, but it's times 0. That's because I'm plugging in the next of these numbers here, right? I started with 0, very first one. The next one was a 1, that went here. The next one was a 0, that goes here. I hope everybody's sort of connecting the dots here. I'm taking these numbers and making them here, 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 right? What's the next one? Plus 1 over 3 factorial times negative 1, right? That was the third derivative. What's the next one? It's another 0. The next one will be 1 over 4 factorial times 0. The next one is a 1 over 5 factorial times a plus 1, etc. All right? We use these coefficients up here. You have to also include the factorial thing when you actually write the real series. And I'm sorry, I forgot to write the x's. I chastised somebody as I was walking around. These are the terms, but you should put x, and then this one gets a x squared. This one gets a x cubed. Sorry about that. Can you squeeze those in? They are, of course, important Each one of those things that I wrote is the coefficient in front of x to some power. I got to put those powers in, all right? So if I write this a little bit nicer, just sort of leaving out the zeros, the very first thing I see here is x, right? A bunch of ones in front of it, but x. Then this is 0. The next one, 1 over 3 factorial times negative x cubed. So that is minus 1 over 3 factorial x cubed. The next one is 0, because I have a 0 in the next one. The next one is plus 1 over 5 factorial x to the 5, etc. Anybody see the pattern here? What's the next term if I were to write the next term in there, going by the pattern? Yeah?
Would it be minus 1 over 7 factorial x to the 7?
I like that. Yeah, minus 1 over 7 factorial. I wrote x to the 5. X to the 7. The next one would be plus 1 over 9 factorial x to the 9, minus, etc. Right? So the Taylor series for sine has only odd powers and alternating plus minuses. All right? This is the Taylor series for sine of x. This is something that you should memorize. It is one of the very basic, and did I say? You should also remember the one for e to the x. So I'm going to go up and put it in a box. Boop, 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 boop. Here, this is the series for e to the x. All right. This is the series for sine of x. Very important. This is, like I said, the whole, what's interesting to me about the Taylor series is it gives you another way of thinking about what sine of x really is. What it is, from this point of view, is it's an alternating series of only odd powers of x. All right? And actually, something cute about this is, even if you have never heard of sine of x before, even if you don't know anything about triangles or opposite over hypotenuse, that's the typical definition of sine of x, you could actually tell some kid, this is what sine of x means, and then that kid could actually figure out some properties of this function. For example, just looking at this, you can tell that sine of 0 equals 0, because if you plug in 0 on the right-hand side, everything will become 0. You can also tell things like, in this case, we can see that sine of minus x equals minus sine of x. That is to say, sine is an odd function. It's because if you were to plug in negative x for all these x's, since these are all odd exponents, that minus sign would factor out as it would inside of any odd exponent. All right. What I'm trying to say, I mean, this is not really earth-shattering, but what I'm trying to say is, when you understand the Taylor series of a function, it actually lets you understand new properties that you might not have known about beforehand just by looking at this. And it's easy to tell, this is a true fact in general. Any odd function, when you write its Taylor series, will have odd exponents everywhere. And any even function will have even exponents everywhere. Isn't that cute? If I wanted to write this as a summation, it's a little weird because it only has odd terms in there, but here's how you would do it if you really wanted to. Now, I wouldn't suggest going crazy with this point of view, but I would write it something like, how about the sum n equals 0 to infinity. I'm going to write the x's, it's only odd powers, and I'm going to make that happen like that. So instead of saying x to the n, I say x to the 2n plus 1. This is so that you always get an odd number inside the exponent. If it was just 2n, it'd be even every time. But when I add 1 every time, it's going to be odd every time. And then what else needs to go around it? We also have the 1 over that same number factorial, and we have the alternation of the sign. To make that happen, I'm going to go minus 1 to the n. This alternates the sign. And then to get the proper factorial in the bottom, it's that same exponent, 2n plus 1 factorial. All right. So this, if you really, I would not suggest trying to memorize that formula, but this is how you would write it as a summation if you really wanted to. All right. A few minutes left. Can we just write out the same thing for cosine? It's almost the same, although every little detail is different. But can we do the same for cosine in our remaining 5 minutes? So I would start again by writing out my derivatives, enough of them so that I can see a pattern. It's, like I said, it's going to be very similar, but everything will be slightly different. So the derivative cosine is minus sine of x. The second derivative would be minus cosine. The third derivative would be, the derivative of cosine is minus sine, so this actually would be straight up positive sine x. And then the next derivative, I'll get cosine again, and I'll be sort of in this same sort of a loop of 4 things, this cycle of 4 different answers which are going to repeat themselves, right? Those are the derivative functions. To get the coefficients that we're after, we are going to plug in x equals 0 for each one. So I go f of 0, cosine of 0 is 1. Next one, f prime of 0, that would be negative sine of 0. That's 0, right? Because sine of 0 is 0. Next, negative cosine of 0. That's negative 1, because cosine of 0 is negative 1. Next, I have sine of 0, which is 0. And these 4 numbers will repeat again. So it goes 1, 0, minus 1, 0, etc. Right? So the pattern this time, it's almost the same. I mean, what we had before was the same numbers, just the cycle where the numbers appear is slightly different, right? This time it starts with a 1, and then has a 0, then a minus 1, then a 0. Okay, so what is our series going to look like? So the series is cosine x is, okay, the first term this time is not a 0, it's a 1, because f of 0 is 1. So the first term is a 1. Next, 1 over 1 factorial, 0 x to the 1, right? I put 1 over 1 factorial, that's just always part of the coefficient, and then 0, because that's what f prime of 0 was. And then x to the 1 is the power of x. Next, 1 over 2 factorial. The next coefficient that I see up there is negative 1, and then x squared. The next one is 1 over 3 factorial times 0, x cubed. The next one, 1 over 4 factorial times 1, x to the 4, etc. All right. This is very much like the formula for sine. It's just everything is in a slightly different position. All right. So if I sort of simplify this stuff and leave out the zeros, what do we get? We get 1. The next thing is 0. I'm going to leave it out. The next one that's not a 0 is this one here, which is negative. So it's 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4. The next one will be minus 1 over 6 factorial x to the 6 plus, etc. So this is the series for cosine. It is, again, alternating signs. Maybe I'll just write them next to each other just so that we can compare. The sign is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5 minus 1 over 7 factorial x to the 7. Right? These are the Taylor series for sine and cosine. They are similar in that they alternate plus minus signs, and the exponents, the degrees, always go up by 2. So cosine has all the even powers, sine has all the odd powers. All right. This, I feel like, I wish I could have been the guy who discovered this. To me, there's something really sort of truly beautiful about this fact. Just because the original people who invented sine and cosine, or like the ancient Greeks or whatever, they had no idea about this stuff. And they did not intend for this to be the case. But it turns out by some kind of magic that sine of x and cosine of x, when you write their series, it's not the same, but it's like they are somehow, they go really nicely together. They make a cute couple in a way. One thing that I would immediately think about is, what if you add these together? The cosine has only the even powers. The sine has only the odd powers. If you add them up, you get all the powers. Does that sound familiar to anybody? Actually, if you get all the powers, that's this, right? This makes me think maybe there's some relationship between sine and cosine and e to the x. Maybe they're kind of like all kind of the same thing, just rearranged. This is a truly deep thought, and this really, nobody in history would have expected this, because e to the x as a function is not at all related to trigonometry, sine and cosine. At least it shouldn't be. I mean, there's no reason to think that it is. It turns out, and we'll talk more about this, actually there is a relationship, and there is a formula. I don't know if you've ever heard of this formula. There is a formula which relates sine and cosine to the function e to the x, even though such a thing, there's no reason to think that's even possible, but actually it is possible. All right, that'll do. Thank you for listening to my little speech at the end. I hope you enjoyed my cool story. See y'all tomorrow.